We're now in section 2.3, which is a topic called linear regression. And before I even tell you what regression is, I want to talk about 3 different scenarios. The first scenario is you're a small business owner. The second scenario is you are a medical researcher. The last scenario is you're a child development researcher. Now, each of these cases, we're going to look at scenarios where you have some data that you want to analyze and you want certain questions answered, especially as you research or as you're, trying to grow your own business and dollars are really important. In each of these scenarios, there's going to be data that we want to analyze. So as a small business owner, the thing that you want to analyze is the amount of money you spend monthly on advertising versus your monthly revenue. So maybe you own like a roofing business and you're spending some money each month on Google ads or Yelp ads, and you want to know, is that advertising money really translating into revenue? And so you track it for a few months, maybe for 4, 5, 6, 7 months. You keep track of how much you're spending on that advertising and how that's translating to revenue. And say that you're a medical researcher and you want to analyze the amount of a drug versus the number of cancer cells that it eliminates, or the number of cancer cells that are left. That's the thing that you can measure. And so maybe you perform a study where a certain group of people you give this level of the drug, another group you give a different level, and another test group you give a different level, and you see how that translates into eliminating cancer cells. So that would be important data to be able to analyze. And then a child development researcher might want to analyze something like the number of minutes read to at night versus a person's high school GPA. How many minutes were they read to on average as a child? Does that predict certain academic achievement? And so for a study like this, you might have thousands of different data points. So imagine a table with just thousands of data points. And you want to interpret that and analyze it in a way that you can predict things. And so this is a question we can ask. There are all sorts of times when a lot of data is collected. Any researcher is going to collect a lot of data. This happens over and over again, thousands of times a day throughout the world. And you want the ability to predict with this data. What is this data telling you? But the data may not exactly be linear, but sort of look generally linear. You can imagine with thousands of data points, they're not all just going to line up in a straight line. Is there a way to fit a line to the data that closely resembles the trend of the data? And so this is the idea behind linear regression. We're going to take sometimes massive amounts of data, and we're going to find a line that best fits the data. And we're going to use technology to do this. In particular, in this class, we're going to use Desmos to do it. We don't have to do the actual calculations, the arithmetic to do this, and it's very tedious. But we're going to use Desmos. We do need to know the process to use Desmos, but Desmos is really going to do the hard work behind the scenes. But once it gives us a best fit line, this linear regression, we need to be able to interpret what's going on and if it really is a good fit, and then be able to do what we really want to do, which is predict with that linear regression model. So imagine you have tons of data and it's either in a table or maybe you've plotted it, and these are all the data points here. And they certainly don't all fit on the same line. They're all over the place, and maybe you have a few outliers. But in general, it kind of does fit a line. You can see that the trend is sort of this way. And so linear regression is going to help us to find the equation of this line, which is so powerful and will give us the ability to predict things. Our first example is going to be related to carbon monoxide pollutant concentrations as a function of year. So let's read through this situation. Carbon monoxide pollutant concentrations. The data in the table show the carbon monoxide pollutant concentration. So I guess that, to me, that sounds like just carbon monoxide floating in the air, which doesn't sound like a great thing. Obviously, it's a pollutant. Okay, so that stuff in parts per million, that's the unit of the carbon monoxide concentration for years since 1990. The data are based on 359 monitoring stations from various locations in the United States. Okay, great. And here's the data. So years since 1990. So in 1990, that concentration was 6 parts per million. 5 years later, the concentration was 4.7 parts per million. And we can see as the years go up, it's not all evenly spaced, but the years are going up, and that carbon monoxide concentration is going down. And our first job is going to be to find a linear regression model for this data. So this will be a linear function that is the best fit for the data that they've given us. All this data, if we plot it, it won't be in a straight line. But what we're going to find is the model that is the closest thing we can get to a straight line based on these points. It's the straight line whose distance from each of these points is minimized. And we're going to use Desmos. Okay, I have a totally blank graph here in Desmos, and when I want to ask Desmos to perform a linear regression for me so that I don't have to do all the calculations, all the arithmetic involved in what is a very long process, I first tell Desmos I'm going to input the data. So I put this or click this little plus sign, and importantly I need to go to where I'm going to enter a table. And I should have x1 and y1. Make sure they really are x1 and y1 up here. If not, you need to change them. Otherwise, the regression won't work. And I'm just going to put in my data, 0, 6, 5, 4.7, and I'm just tabbing in between here. 3.9, 10, 3.4, 11, 3.2, 12, 3, 13, 2.8. And I just do a really quick check to make sure I've input my data correctly. Most often, if students get something wrong on regression problems, it's because they've input the data, you know, just there's a typo somewhere. Okay, looks like my data is all good. And here's some of it over here. It's not all showing up on my screen. So an important tip is this little magnifying glass will fit this data into your window view. So I'm going to click this zoom fit button, and great. Okay, so all the data is here, and we can see that it's sort of following the trend of a line, but all these data points aren't exactly sitting on a straight line. So we're going to find the straight line that's closest to all those points. And the way that I do that is I go to the next line and I tell Desmos, okay, I want y1, and I just plugged in 1. It knows to put it as a little guy. And then this tilde right here is the operation. It tells Desmos that I want to perform a regression, and now I have to tell it what kind of regression. Later in the semester, we'll perform other types of regression. If our data doesn't look like a line, we need to maybe do a quadratic regression or an exponential regression, different types of functions to fit the data. But for right now, we're just talking about linear functions. Everything's sort of, you know, the starting point. So we're fitting everything to a line. And let's see, a line should look like y equals mx plus b, and we're going to use ax1 plus b. And so I use x1 and y1 because that's what the data in the table are labeled. You don't want to use x and y. That for some reason Desmos prefers that we use x1 and y1 when we're doing these regressions. The tilde tells Desmos that we want to do a regression, and the form that I give it is of a line. And so then it shoots out a bunch of numbers. Okay, so this is awesome. It has given me the line that looks really close to all that data, and this is a line that I could predict. Like if I wanted to know, you know, instead of the points that I already measured, if I wanted to know 18 years out or even 20 years out. Now we can see how the model starts to break down because you can't have negative concentrations of that carbon monoxide. So models aren't perfect, but this is a pretty good model that shows the trend of how things are decreasing. Okay, so let me show you some important numbers. The A here is negative 0.248, and that's what will be in our the A in our linear regression model. The B is 5.986, and that is the B here. So these two numbers, these parameters, will tell us what the line is. And in a minute, I'll tell you about this r squared number. It's an important number too. So now that I have this linear regression model, I'm going to go ahead and write it out. Desmos has found it for me, but I need to put all the pieces together. And Desmos tells me that my linear regression model should be y equals, let's see, our a is negative 0.248x plus our b is 5.986. I'm going to rewrite it using the variables that were given in the data table. And so that would look like p of t equals negative 0.248t plus 5.986. And this is it. This is the linear regression model. And with it, we are able to answer a whole series of questions. But we've done the thing that they asked us to do first. We found the linear regression model. The next thing that we may be asked to do is to interpret the slope of this model. And here's the slope right here. Okay, so if I want to interpret the meaning of the slope, first I need to write what the slope is. The slope is negative 0.248. And what does that mean? So typically what slope means is for every 1 unit I go over on the x-axis, I can expect to go this much on the y-axis. So let's see, let's zoom in here. Okay, and for every 1 that I go over on the x-axis, so I'm going over 1, to get to another point on the line, you would go up or down depending on if your slope is positive or negative, that much. And here it's reasonable that I've gone down 0.248. You know, if you think of this right here is 5, and this is 4.5. So I've gone over 1 unit and down negative 2.48. And that'll happen again and again. So every year that I go forward, I'm going down negative 2.48 in that CO, that carbon monoxide concentration. And so this is the interpretation of the slope. For every year, the carbon monoxide pollutant concentration goes down 0.248 parts per million. So every year, the carbon monoxide pollutant concentration goes down by 0.248 parts per million. This is something that we really want to start getting comfortable with. You know, we're moving into the realm of math where we really need to interpret our results and what do these numbers each mean. So being able to interpret slope in a variety of contexts is a really valuable skill, and this section is going to help us get better at it. But remember that a slope tells you if you're going 1 unit forward on the x-axis, what is your y value doing? Well, in this case, it's going down by 0.248. Okay, the next thing we're going to look at is what does this number here mean? So we're asked to interpret the meaning of the vertical intercept, and the vertical intercept will be 5.986. And so let's think about what that means. Well, this means that in year 0 or in 1990, that the concentration is going to be 5.986 parts per million. So this is interesting. The linear regression model actually predicts something different than what the data table tells us. And that's okay, because this line of best fit will not always hit all the points exactly. the model has to compensate in some ways. And so this is what the model is telling us, even though we have different. And so we'll say that the meaning is the model predicts that in 1990, the carbon monoxide pollutant concentration is 5.986 parts per million. And that's the meaning of the vertical intercept of this model. So this guy right here. Before we leave this page, I want to talk about this R-squared guy. So we get the parameters. These are the really valuable things that Desmos gives us after we've input all the data. This is what enables us to construct the model. But they also give us some other information. And what one piece of information that we're going to tap into or at least notice is this R-squared number. R-squared is called the coefficient of determination, and it is a measure of how well this line will actually fit the data. You know, you can imagine sometimes being given data maybe that doesn't look anything like a line. Maybe it's a mess like this, and they'll try to construct a line that minimizes distance between all the points, but really it's not a great measure for that particular data because the data itself doesn't lend itself to being represented as a line. And we got lucky. This data really did look close to a line, but this coefficient of determination is an indicator of how well the linear regression model fits the data. And when it's really close to 1, like this one is, it means it's a good fit. So the coefficient of determination is a number between 0 and 1, and the closer that it is to 1, the better fit the data is to a line. And if you had something like R-squared equals 0.43, that's not really a good fit. And you're like, well, I don't think this data really is linear data. We better look for a different type of model. Or if your R-squared is, say it was 0.7, you'd say it's pretty good, but perhaps there's a different type of model, maybe a quadratic function, which we haven't talked about yet, but we will, or some type of exponential function that might model it better. But if your R-squared is definitely in the 0.9s, then it's a pretty good fit. Even a 0.85 isn't terrible. So R-squared is a measure for how well the line fits the data, and it'll always be a number between 0 and 1, and the closer it is to 1, the better the fit. I want to answer a couple more questions with this same example, and so here's the model that we found that we'll use to answer these next two questions. So we're now asked to predict P of 7, so predict the pollutant concentration when 7 is our input, and then we're going to interpret the results. And one reason we're trying to predict it is because 7 was not a given value. We don't know what happened in 1997. So we're going to use the model that linear regression gave us to predict what happened in 1997. And P of 7 will equal, just using the model, 0.248. Our input isn't T, it's 7 now, plus 5.986. And so P of 7, I just got to use my calculator and figure out what this number is. And I found out that P of 7 equals 4.25. Now we're asked to interpret our results. So what does it mean for P of 7 to equal 4.25? Well, 7 is, let's see, is that a year or the pollutant concentration? That's definitely a year because it's our input. So in 1997, the pollutant concentration was 4.25 parts per million, and that lines up pretty well with the data because it is, it was going down, and from year 5 to year 9, we would expect year 7 to be in between those two. So in 1997, the carbon monoxide concentration was 4.25 parts per million. Next, we're asked to predict P of 15, and if we go to our table, yeah, 15 it's actually off the chart. It's not even within the data set. So we're going to predict what would happen 15 years after 1990. What would the carbon monoxide concentration be? So P of 15, we still use the same model, negative 0.248, but this time our year is year 15 plus 5.986, and I find out what that number is. And I find out that P of 15 is 2.266. Let's just see if that's reasonable. That seems pretty reasonable because in year 13 it was 2.8 and it was going down. Okay. So, and then the meaning of this, let's see, 15 years after 1990 is the year 2005, the CO concentration. The model predicts it will be 2.266 parts per million. There are two important words we need to talk about, interpolation and extrapolation. Interpolation is when we're trying to predict output for an input that falls within the, between the minimum and maximum of the data set that we're given. So within the min to max of your data set. Inputs. So for example, if we were trying to predict a number between 0 and 13 that maybe wasn't here, like, like the number 8 or the number 11.5, that would be an example of interpolation. And then extrapolation is interpreting or predicting output for an input that's outside of the given range of inputs. So we can look back on our examples and ask, was this an example of interpolation or extrapolation? So was this interpolation? Interpolation or extrapolation? And because in the data our inputs went from 0 all the way up to 13, 7 lies within that range. So this is an example of interpolation. And then we can ask the same thing for part E here. Was this prediction an example of interpolation or extrapolation? This time the input, 15, was outside of the range of the given inputs. And so because it's outside of the given range of inputs, this is an example of extrapolation. Two different types of predictions. Our last example for this section, we're given a linear regression model. And this model models men's 400 meter in the swim, like freestyle swim, winning Olympic times where Y is years since 1924. So W is the winning time based on the year. And we can see the slope of the function here, the vertical intercept here. Why would you think the slope of this model would be negative? So that's the first thing we're going to think about, is they ask us to interpret the slope. So if we think of what's going on in this graph, the inputs are years and the outputs are winning times. So the slope says for every year forward I go, that my winning time, the Y value, goes down 1.17, and we'll assume this is in seconds. So that's essentially what the, this line looks something like this. So for every year I go forward, I'm going to go down 1.17 seconds in my time. And that makes sense because swimmers' times are getting faster. So with the Olympics, you might even think of, well, what happens every 4 years? Well, every 4 years it goes down about 4.7 seconds. So every Olympics. So the slope tells us every year we would expect the winning 400 meter times to go down 1.17 seconds. And then we're asked to interpret the vertical intercept. So this is a common thing that we're asked to do. The vertical intercept for this function is 301.88. It's where your input value is 0. So if this were 0, that would all go away. And so our output value would be 301.88. And the interpretation for that is, let's see, this is years since 1924. So in 1924, at the beginning, when time or year equaled 0, the winning time was 301.88. Okay, in 1924, the winning 400-meter time for men's was 301.88 seconds. And the big ideas from this section are we want to be able to use Desmos to create a linear regression model, just given a table of values of data. And we want to use that model that is created to predict things, to predict different outputs, to also be able to interpret what the slope and the vertical intercept mean. Also along the lines, we learned these two words, interpolation and extrapolation.